Hello, welcome to your first notes video for Math 1313 College Algebra. My name's John Cowan. I'm one of the math faculty here at HCU. I might not be your teacher if you've already seen in some of the videos or correspondence you've had with your instructor, but for these notes videos and the completed notes and the blank notes and a lot of the activities that we'll be doing throughout the year, you might see my face or hear my voice. I would encourage you to watch through those videos just as if they're your instructor. And then reach out to your instructor if you have any questions or comments, or if you find an error in the videos or the notes, and we'd be happy to fix them. So without further ado, let's go ahead and get started. We're going to start today, and this is kind of a way to start every day, is to reflect on Scripture. Sometimes it'll be super applicable to what we're learning, sometimes not so much, but still good to reflect on. So Proverbs 25 says, it is the glory of God to conceal a thing, but the honor of kings is to search out a matter. And that's kind of exactly what we're going to be doing today, taking some things that might be a little bit difficult and searching them out. So let's get started. This section, titled Linear Equations, is all about this word, line. It's about equations that make up lines. Most of today's things are going to be expressions and not necessarily functions or graphed functions, but just one line, one variable, one equation across the board. Some of them will look pretty familiar and some of them might look a little bit difficult. So just to get started, we're going to look at something probably reminiscent of high school, and we're going to look at a normal linear equation written in general form right here. The general form just meaning ax plus b equals c, where we can see that we've got a bunch of coefficients and constants and one variable that we're going to be solving for. So often you'll see this, and I'll do this pretty much every problem, is draw a line down the middle. The lines to remind us what we do to one side, you have to do to the other side. And so in order to get x by itself, we're going to work backwards through PEMDAS to try to isolate x. So if you think about PEMDAS and you think about parentheses, exponents, multiplication, division, addition, subtraction, we're kind of just going to work our way up instead of down that pyramid. Starting with subtracting 1 from both sides, because 1 minus 1 is 0. And what that'll leave us with is just a 2x on the left, because the 1 minus 1 goes away or turns into 0. And now we have to evaluate negative minus a negative. So negative 9 minus 1 gives us negative 10. And then we take a second step. So this is a two-step equation or two-step linear equation, where we're going to take a second step to divide both sides by that 2 that's keeping the x from being by itself. And we're left with x equals negative 10 over 2, which is negative 5. And there's your answer. The x that solves this problem or this linear equation is negative 5. I will write all of our answers whenever they can be written this way in set notation, which says I'm just writing a complete set of the answer, the set of the numbers that is negative 5. And so that was solving a linear equation with one variable. Let's move into one that's a little bit more difficult, only because it has more things going on. Not because any of the single steps that we're going to do are that much more difficult. First, I'm going to do this. I'm going to draw a line down the middle to remind me what I do to one side, I need to do to the other. I'm going to look at this linear equation. I'm going to say, looking at this multiplication, this invisible multiplication on the outside, and the parenthesis set there, I'm going to do a thing that you may be familiar with or may not, called the distributive property, which is to just multiply both the terms of the inside by that negative 2. This only happens when we have addition or subtraction on the inside, and multiplication distributes to it. We'll explore more of this distributive property with exponents at a later time, but for right now, the distributive property distributes multiplication across that addition or subtraction in the middle. And so when I distribute, I get negative 2 times 3x is negative 6x's. But then I need to also distribute it to this. So negative 2 times negative 1 is a positive 2. And this x over here remained untouched because it didn't distribute anywhere the parentheses weren't. And I'm going to say equals 14 minus x. And now my goal is I'm going to move all the x's to one side and everything else to another side. So let's see. I've got, and I might change the colors here, I've got this negative 6x and this x, which can combine together. This idea of combining like terms to give me a negative 5x. That plus 2 didn't get combined because there was nothing to combine it with, equals 14 minus x. And now I still got two x's and I want to turn them into one x. And so the way we're going to do that is we're just going to move this x over to this side. What you do to one side of the red line, you have to do to the other. And so now I've got negative 5 plus 1. There's an invisible, just like there was an invisible multiplication before, there's like an invisible 1 hanging out in front of that x as an invisible coefficient. So I'm going to end up with negative 5 x's. I stole 5 x's, and then I gave 1 x back. So now I have negative 4 x's. And I still haven't touched this 2. I'm doing everything one step at a time. Later in the year, we'll probably move a little bit faster through the steps, but for right now, we'll go one step at a time to show you exactly where each thing happened. Next step, I need to move this 2 over. So what I do to one side, I have to do to both sides. And I get negative 4x is equal to 14 minus 2 is 12. And if you could guess the last step, it's going to mirror what we did in the problem up above. We're going to divide by that last coefficient. And get x is equal to negative 3. You can zoom out so you can see the entire problem for a second. If you need to pause it, feel free to pause it. And then I'll write my answer inside of a set to let you know that negative 3 is the x that solves this equation. If you wanted to check this answer, you could take this negative 3, plug it into x, plug it into x, plug it into x, and make sure that what you get at the end of plugging it in and working them all out is correct. All right, we're going to look at a second type of equation today called a rational equation, and you'll notice a pretty serious difference between these. You'll notice the location of the x's has been moved to the bottom. It's okay, it's nothing to worry about. Our goal is just to turn it into the first type of problem. So it looks like the x's are on the bottom. We're going to try to move them to the top and then use the skills from those first two problems to solve through it. And the way we're going to do that is we're going to identify an LCD, or a lowest common denominator, or some denominator that we can use that all of these terms are a factor of. And so, for instance, you might want to pick a 3, but 3 does not have a factor of 6. And so 3 would not be a factor of every single denominator. You might even pick a factor of 6 and try to think of the factors of 6, which would be 1 and 2 and 3 and 6. But what you'll see is 4 is not a factor of that. And so picking this lowest common denominator that we're going to change them all to is really important, that it will cancel every single term. So what's a number that 3 and 4 and 6 are all factors of? The lowest one we can think of is 12. But you'll notice that those denominators aren't just numbers, they also have variables. And so in order to cancel out those variables, I'm going to put an x with that lowest common denominator, because 12x has a factor of 3x, 4, and 6x. It's going to take some practice to identify those lowest common denominators. So practice your homeworks doing it, read through the book and some example problems. But picking that LCD is going to take a little bit of practice before you get good at recognizing it. So here's what I'm going to do. With that LCD, what I'm going to do, draw my line, and I'm going to multiply both sides by that LCD. 12x, 12x, and I'm just going to see what happens. So if I zoom in here, 12 times 2 would make 24x over 3x. That's going to reduce and simplify. Here we go. We have this distributive property of cross subtraction happening again. This is going to keep happening, and another important skill to practice. So 12x over 4 minus 12x over 6x. And what you'll see is if you picked your LCD right, then you'll get a lot of reduction happening, and the bottom, or the denominators, will all just disappear. And if you didn't pick it right and the denominators don't disappear, that's okay. Maybe start from step 1 and pick a different LCD. So 24 divided by 3 is 8, and x divided by x is 1. So technically you have an 8 times 1, or just an 8 underneath it. 12x divided by 4 is 3x. The x did not disappear there because there wasn't one on the bottom. Minus, and 12x divided by 6x is 2. And now it looks like a problem just like the ones from up above. So we're going to solve it exactly the same way. I might try to go a little bit faster to save you some time. Plus 2 gives you 10 equals 3x. The next step is the same last step of dividing that last coefficient that you had left over. And so we've got x on a different side, but that's okay, equals 10 over 3. And I'll write that inside of my set to let someone know this is the only answer to that equation. I'll zoom out a little bit so you can pause it if you need to. And that was solving rational equations when the x's are on the bottom. Now before I move on, I want to make one quick point about my answer. 10 over 3 is a great answer here, but we did something kind of sneaky in the middle of the problem that's worth noting. And if you look at the online completed notes, you'll see that this note keeps showing up. When we did this multiplication fact and this reduction step right here, some things that used to be on the bottom kind of disappeared or canceled off the bottom. So before doing that step, or at the end of your problem when you get your solutions, wherever you do it, doesn't matter, but it matters that you do this. We are going to consider the bottom and think about a rule back from the 3rd or maybe even 4th grade that your teacher said was a really bad thing and you're not allowed to do. Your teacher probably said you cannot divide by, if you said 0, you're right. You cannot divide by 0. And so what that means for us in this problem is before we eliminated those x's from the bottom, we needed to just think really carefully about x cannot be any number that would make the bottom 0. And so in this case, the only numbers would be 0. If you want to see like a solve for that, we would just take the bottom and say 3x, you better not be 0, and then solve that as x is not 0 over 3, but that's just 0. And the same thing with the 6x. But we make a note saying, hey, x, you're not allowed to be 0. But you'll see when we look at our solution, 10 over 3 is not 0, and so we were good, and our solution's an accurate and valid solution. Just worth noting somewhere in the problem, whether once you get your solution set or in the moment, like where that green arrow is, when you eliminate the denominators, you need to be really careful to consider, oh, did I eliminate a potential bad number or domain restriction where x cannot be this number? But because x wasn't that number, and x here at the bottom was 10 over 3, then we're good with our solution. Okay, we're going to move to a slightly harder one. Sometimes in these videos, you might see me skip over some try-its. That's a chance for you to go home and try them on your own. They'll all be completed in the completed notes section. So if you want to go and look and make sure you got it right, you can go on to Canvas and check the completed notes section. But we're going to skip over this so we can do one that's a little bit more challenging. When it looks like the denominators don't go together at all. But what we're going to see is these actually do work pretty well together. So I'm going to draw my red line, and it's the same type of problem. Solve the rational equation. And I'm going to manipulate that right side just a little bit. And if you remember factoring, whether it's from 1302 at this school or high school, then you might remember that you break down the last term and do all of its factors, which would be -1 and 2, or -2 and 1. And you say, do any of those factors add up to this middle number? Well, yeah, this one particularly does. If you add up those two numbers, -2 plus 1 is -1. Really not the x included, just this coefficient, this invisible -1 right there. And so this term factors nicely into 1 over x minus 2, x plus 1. And what you'll notice is those are the two denominators from the other side. And so you could imagine picking an LCD like we did in the last problem that will nicely take care of all of the denominators, whether it's on the right side or the left side. And so even though this is an ugly LCD, the math and the canceling and the working out is not going to feel that ugly once it gets plugged in. So I'm just going to pick that big denominator as my entire LCD, and then I'm going to go to my equation and multiply both sides by it. And what you'll see is, again, a lot of canceling happens. Oh, here we have the distributive property once again happening. I'm telling you, every single problem is going to have distribution. It's just a property that happens a lot. So if you don't feel good about it, you could Google or go to chat or go to any AI model and say, give me a bunch of practice problems on the distributive property so I can get good at it. But it's going to happen a lot. So on the right side here, we have all of the terms canceling. X minus 2 cancels and x minus 1. Oh, I wrote that wrong. You might have been yelling at your computer. Hey, you forgot the plus sign. Because this, what I say in my LCD, yeah, it's supposed to be plus 1. So those two terms cancel. Notice it's not 0. Anything over itself is 1. And if we distribute this term, we should get 2, x minus 2, x minus 1 over x minus 2 plus 1 times all of that is just all of that, x minus 1 over x plus 1, and you'll see some other terms canceling too. Those cancel and those cancel. And when I say cancel, it's not a good math word to say cancel. I probably mean turn into 1 because anything over itself is 1. And so we're left with 2 times x minus 1 plus x minus 2 equals 1. And you might see something here. This looks like the first problems. This looks like problem set 1 and 2 that we did a second ago. And it is. The goal of this is to turn them into the original problems. I will make that note here instead of at the end. It's okay to do it either spot, but I will say we just got rid of some denominators. And so are there any x values that would have made the denominators bad? Well, sure. X better not be or cannot equal 2, and x cannot equal negative 1. And so if we get to the end of the problem and we see those in our solution set, then we need to not include them and say this was not allowed on the domain of the original function. Other than that, this is going to be a problem that we're going to solve exactly like those first ones. So I might go a little bit faster here, a little less color control. We're going to distributive property that. And we're going to write it without parentheses set on that side. Anything that matches, we're going to combine. So we have 2x combining, and we have, those two terms combining. Oh, did I do it again? I wrote minus 1. It's supposed to be a plus 1, isn't it? Plus 1, plus 1, plus 1. I don't know why I keep wanting to write that negative 1. So that would be 2x plus 2. You'll see these red terms cancel. Positive 2 and a negative 2 turn into 0. And 2x plus x is 3x equals 1. And so if we have that same last step of dividing the coefficient over, we'll have divide by 3, divide by 3, and so x is equal to 1/3. I'll zoom out for a second so you can look at the problem. Pause the screen if you need to pause it to look at that solution and be careful with it. Oh, maybe check too while it's zoomed out. Was that any of our bad solutions or domain restrictions? It wasn't, so it's a good answer to report. All right. Now we're going to move just a little bit faster paced stuff. Just some definitions and types of equations to see. We'll do that, and then we'll wrap it up for today. The first definition we're going to use is the slope, a formula you've probably seen before, which is y2 minus y1 over x2 minus x1. If you want to go ahead and memorize that and commit it to memory, it's an equation that will come up all year long. And so to use the slope equation, we're going to take our 2 points. We're going to label them as x1, y1, and maybe in a different color, x2, y2. And then we're just going to plug them in straight into this formula. So the slope is equal to y2 minus y1 over x2 minus x1. And so if we take our numbers from up above, we're going to say that's 4 minus 6 over 1 minus, and notice these parenthesis sets that I'm writing here. I'm writing those parentheses around them because I want to be really careful with those negative signs. And the parentheses help you know which negative sign you're on, whether you're talking about the negative 2 and the negative sign in front of that, or the minus sign in the middle. And so 4 minus 6 is negative 2, divided by 1 minus a negative 2, if you remember your subtraction properties, is negative 2/3. And that's your slope. That's not a solution for x, so I'm not going to write it inside of set notation, because it's not saying the set of the numbers that solve this problem. This is just asking what is the slope through these 2 points? Another formula, which is derived from the slope formula. Notice if you just move this term from over here, it looks a lot like that slope formula. And it's the formula for a line given a slope and a point. And so it's going to be very similar to the last one. We're going to plug in our numbers where we see them in the equation. Y minus y1 equals mx minus x1. I'm going to label my points that they give me as x1, y1. Notice there's not a second point because this equation doesn't call for it. They're actually going to give us the slope up above of 4. That's our m value. And we're just going to plug all those numbers in where we see them and be done. So y minus y1 is 5 equals, there's a blue 4 from up above, 4 times x minus 2. And that's the point slope formula. Point slope form. Now you might see that in the problem they asked for a different form, the slope-intercept form. This is the form that you've seen for all of your life anytime you've dealt with lines, the y equals mx plus b. Y equals mx plus b. And what we're going to do is solve this problem just like the rest of the solves today, the try it 1, the try it 2, the try it 5, or whatever we skipped to. We're going to use all the same skills to solve this problem. So we're going to use the distributive property first. Maybe we could even draw that line through the equation to see this is just like the other problems. So we're going to distribute that 4, get 4x minus 4 times negative 2 is negative 8. And then we're going to get y by itself. So how do we get y by itself? Add 5 to both sides. And we're going to end up with 4x minus 3 as a second equation. So these two highlighted equations are the exact same line. These equations define the same line on the same grid. They're just two different ways to write that line. This one is the slope-intercept form, and the first one was point-slope form. The reason it's called point-slope form might be obvious. It contains a point, x1, y1, and a slope right there, m. The reason this is called slope-intercept form is because it still contains that slope right there of 4, but now it's going to indicate your y-intercept, which we haven't talked about yet, but your y-intercept of 0, negative 3. All right, the next one is kind of pretty similar, so we're going to skip it and let you try it at home. And we're going to look at this mnemonic device, or this memory device that can help you remember when the lines are actually a little bit easier to find of lines. So this Hoy Bucks here, I don't know, my 6th grade teacher gave it to me, and I haven't forgotten it since, and it helps me remember that H, O, Y go together, so horizontal line, 0 equals the slope, and Y equals blank is your form. Hoy, horizontal, 0, Y equals form. VUX is vertical, undefined slope, and the format is going to be x equals blank form. And so what I'm going to do here is I'm going to find an equation of the line passing through these 2 points using one of those 2. It's a little hard to see at first, but if you plot the points, I think you'll probably see, oh, I can get this. So 1, 2, 3, 4, 5, there's negative 5, 1, 2, there's 2. And then 1, 2, there's 2. And if we plot a line through those 2 points, it looks like a horizontal line. And so I'll go with the Hoy, saying this is a horizontal line, and it's going to be of the form y equals. And so y equals what? Well, let's just look at every y value across this problem. We've got a y value here of 2. We've got a y value here of 2. And when we graphed them, we had a y value here of 2. When we graphed them, we had a y value over here of 2. Everywhere you look, there's a y value of 2. And so we're going to say y is equal to 2 is the equation of that line. The equation form of these is a pretty simple equation form. I think the easiest way to do it is to recognize what number's in common and plot that number. So for example, oh, they don't give us a second example. But if I was giving you a second example of 2, 1 and 2, 7, I might say Look at that 2. Look at that 2. Those are in common. What place are they in? That's the x1, that's the x2. So what I know is x is equal to 2, and that's probably a horizontal line. So there's just an extra problem for free. All right, the very last thing we're going to do today is parallel and perpendicular lines. And parallel and perpendicular lines are defined as having slopes that are related to one another. So parallel lines have the same slope. Perpendicular lines have negative reciprocal slope, or so you might see it said opposite reciprocal slope. I like to say, or tell my students to help remember it, flip, flip. You have to flip 2 things to make opposite reciprocals or negative reciprocals. You need to flip the sign. So let me do it right here. You need to flip the sign. So if it's positive, it goes to negative, and if it's negative, it goes to positive. And you need to flip the fraction. So if it was a over b, it turns into b over a. Even if the fraction was a whole number like 3 over 1, you would flip it and make it 1/3. And so I'm going to skip that problem and go straight to the last problem of the day, which is to find an equation of the line. And I might even give you a little extra problem and say also find the perpendicular one too. So parallel and perpendicular to this equation. And so what I'm going to do is I'm going to take this equation, 5x equals 7 plus y, and I'm going to draw my line. It'll be short this time. And I'm going to look for what I need to move over to get y by itself. And so y is equal to 5x plus 7. No, that's not true. That's why you should do your steps. Minus 7, minus 7. So we get 5x minus 7. And there's my slope right in front of the x. You probably could have seen the slope right here too at the very beginning of the problem, but it's good to get it in slope-intercept form. Remember, this is slope-intercept form to see, to know exactly what this line looks like, and they ask you for it so much that it's worth reporting. So now I'm going to write my 2 lines, parallel and perpendicular, and they're pretty easy to write. So I'm just going to say my m, from the original problem, my m was equal to 5. Which means if I use these rules that says same slope for parallel, my m parallel is going to be equal to 5. And those 2 lines kind of mean parallel. Maybe I'll label it parallel. They look like parallel lines, so you might have known that already. And then I'm going to take m perpendicular, and I'm going to say 5 is technically a fraction. There's a 1 on the bottom. And so I'm going to flip the fraction to 1 over 5. And it was positive, so I'm going to flip it to negative. Negative 1 over 5. And then I'm going to use that point slope form that we already talked about. Y minus y1 equals m times x minus x1. I'm going to plug my numbers in and be done, not convert to slope-intercept form. I'm just going to leave it there because it didn't tell me what form to write them in. And so I'm happy writing them in slope-intercept. So it gives us that it passes through this point, x1, y1, negative 1 comma negative 2. So through negative 1 comma negative 2, and I'm just going to plug my numbers in. So I'm going to say y minus y1, or the y value is negative 2, is equal to slope of 5, x minus negative 1. I can flip the signs on both of those double negatives and say y plus 2 is equal to 5, x plus 1. And I didn't tell you which one that was because I wanted you to look at it and decide, do you think that line is parallel or perpendicular? If you said parallel, you'd be right. And then now we're going to do the exact same steps, but the only thing we're going to change is the slope for a perpendicular line. There's an extra problem on that one too, to do parallel and perpendicular in case you see them in your homework. Here's that whole equation. We found parallel and perpendicular lines from an original linear equation based on a point that they gave us to pass through. And if you were to graph both of those, which we'll do later in chapter 4 about, we'd see that those two lines intersect each other at perfect right angles, 90 degrees apart from each other. All right, that's all for section 2.2. Thank you if you watched this far. I would highly encourage you now to look through the try-its that we didn't accomplish, try them on your own, and then look at the completed notes in Canvas to see if you got them right, you got them wrong, where you can learn and where you can grow. I encourage you also, if you're struggling with any of this, to reach out to your instructor so that they can help you and they can encourage you in the process of learning college algebra. Until then, I'll see you next time for section 2.4. Thanks for watching.